Okay, let's go ahead and start. In our last webinar, we talked about the mercury receiver diagram, and part of the diagram that I showed you had this block for the CORDIC in it, where you have the analog to digital converter data that comes in that's 16 bits wide. We have a 32-bit value called frequency, and I'll talk about what that really is today. And then we have the I and the Q data that goes out. So what is I and Q data? Signal modulation involves changes made to sine waves in order to encode information. And here's the mathematical equation representing a sine waves. So here we have a amplitude times the cosine of the frequency with respect to time and a phase. And this is known as this collectively can be known as a phase angle. So frequency is the rate of the change of the angle. So here we have a polar representation of a sine wave. Here we have a vector with magnitude A with some phase, and this phase collectively here is in this cosine statement. So let's look at a statement of cosine of alpha plus beta, and that's equal to cosine of alpha times the cosine of beta minus the sine of alpha times the sine of beta. So when we have A times the cosine of 2 pi ft plus phi, that's equal to A cosine of 2 pi ft times the cosine of phi minus A times the sine of 2 pi ft times the sine of phi. So if we let I equal the A cosine of phi and we let Q equal to A times the sine of phi, we would come up with this equation here. Okay. So you see we have I times the cosine of 2 pi ft minus Q times the sine of 2 pi ft, where I is the amplitude of the in-phase carrier and Q is the amplitude of the quadrature phase carrier. So here we have I and Q represented. So remember that the difference between a sine wave and a cosine wave of the same frequency is a 90-degree phase offset between them. So the implications of this are very important. What this essentially means is that we can control the amplitude, frequency, and phase of a modulating RF carrier sine wave by simply manipulating the amplitudes of the I and Q inputs. With this method, we no longer have to directly vary the phase of an RF carrier sine wave. We can achieve the same effect by manipulating the amplitudes of the input I and Q signals. Of course, the second half of the equation is a sine wave, and the first half is a cosine wave. So we must include a device in the hardware circuit to introduce a 90-degree phase shift between the carrier signals used for the I and Q mixers. But this is much simpler design issue than direct phase manipulation. So here we have our equation with our I times the cosine of 2 pi ft minus Q times the sine of 2 pi ft. So here's the diagram, just sort of a general diagram of a hardware modulator where we have the what we call the in-phase carrier and the quadrature phase carrier, which is 90 degrees out, where we multiply the I and the Q, and then we sum them according to this and produce our RF. Okay? So how do we compute sine and cosine in hardware? Okay, we're going to talk about that today. So this is where the CORDIC function can come in. We can actually do it using a CORDIC function. So let's look at CORDIC algorithms. The CORDIC, or the Coordinate Rotational Digital Computer, was developed by Jack Volder in 1959 as an iterative, and that's important, iterative algorithm to convert between polar and Cartesian coordinates using shift, add, subtract operations only. Okay, no multiplies. And these CORDIC functions are implemented with a shift, add, subtract type algorithm, and we're going to look at the algorithm today and I'll show you how to create it. They can be used to compute trigonometric, hyperbolic, linear, and logarithmic functions. So examples would be sine and cosine, polar to rectangular coordinates, etc. And we're going to look at a particular implementation today where we're using sine and cosine. So CORDIC algorithms generally produce one additional bit of accuracy for each iteration. And I'll talk about these iterations in the design. Some of the applications are like 8087 math coprocessors, HP35 calculator used a CORDIC. Might have it in radar signal processors, robotics, and software-defined radios. And that's where we're interested in today. So, in what's called the circular rotation mode, a CORDIC function could compute the Cartesian coordinates of a target vector v sub n. Okay, here's our target vector v sub n right here. By rotating the input vector v sub 0, this one, by an arbitrary angle, theta. Okay, so this is just a CORDIC function in general, and we'll talk about how we're going to apply it to our application later on, but you first need to understand how to create these CORDIC functions. So here's our vector v0. It's at x0 and y0. And we want to rotate it a certain angle so that we come up with a vector at x sub n and y sub n. So with this CORDIC function, we're going to learn how to do that. So in general, the equation for x sub n and y sub n is right here. X sub n, our final vector, is equal to x sub 0 cosine of the angle between them, minus y of 0 times the sine of phi. And similar, here's the equation for y. So you see that it involves sine and cosine. Okay, we can rewrite that as this form. X sub n equals cosine of phi times x sub 0 minus y tangent of phi. So far we haven't really simplified anything. Well, what good are you thinking this is doing? We still got multiplies and everything in here. However, if the rotation angles are restricted so that the tangent of phi, this term right here, equals plus or minus 2 to the minus, that should be an I. It might be a little hard to see, but that's I. And the multiplication by the tangent term is reduced to simple shift operations. And I'm going to show you how this is done. Okay, so let's assume that we have tangent of phi here equal plus or minus 2 to the minus I. And so in other words, tangent of phi would be values like plus or minus 2 to the 0, 2 to the minus 1, 2 to the minus 2, etc., which would be plus or minus 1, plus or minus a half, plus or minus a quarter, etc. So what is 2 to the 0? Well, that's 1. Okay, right here we are. Here's our tangent of phi is 1. What does that represent? That represents 45 degrees, right? Okay, so if we have 1/2, if tangent of phi is 1/2, what do we have for our angle? We have 26. So here's our, I'm sorry, I said tangent, I meant arctangent. Arctangent of 1 is our 45. Arctangent of a half is this, etc. Okay. Okay, so here we have 2 to the minus I, all these different terms that we could have. We could have a whole table full of them. And these would be the different angles. But you're thinking, well, what good is this? Because these are just specific angles. What if we want to do, you know, 28 degrees? We need a way to do that, not just these ones arctangent of 2 to the minus I. Okay? So here's what we do. The desired angle of rotation is obtained by performing a series of successively smaller elementary rotations. These are our elementary rotations, these 45, the 26, etc. So where I goes from 0 to n minus 1 for tangent of phi equals plus or minus 2 to the minus I. So let's say that our desired rotation is 20 degrees. Okay, we start off with 20 degrees. And the first thing we do is we go through our list of angles here, and if the angle z sub I is greater than 0, then we subtract the tangent of phi angle. Otherwise, we add the tangent of phi angle and also make appropriate x and y calculations. So let's, wait a minute, sorry. Oh. Okay, so we start at 20. Okay, so 20 is greater than 0. So we're going to subtract our 45 angle because it's greater than 0, and that gives us a minus 25. So in our next iteration, the value is minus 25, so we're going to add the corresponding next angle. So we add the 26. And we go through this process of adding and subtracting till we get down to a value of close to 0. Now if I were to go 19 iterations, I would get this kind of accuracy. It would be very close to 0 with just 20 iterations. Okay? So now let's look at our equations again. Here we have x sub n, it's equal to cosine of phi times x sub 0 minus y of 0 tangent of phi. So now we have these tangent of phi values are basically plus or minus 2 to the minus I. So if the decision at each iteration I is which direction to rotate rather than whether or not to rotate, then the cosine of phi of I term becomes a constant because the cosine of I is equal to cosine of minus I. In other words, the cosine of phi sub I is not dependent on the direction of rotation. That's this term here. So the iterative rotation can now be expressed in this form. So our x sub I plus 1, that's our next x, is going to be equal to k sub I times x sub I minus y sub I d sub I 2 to the minus I. And similar for y. So these are our x and y equations. Okay, and k now turns out to be cosine of the arctangent of 2 to the minus I, which is this thing right here. And d, which is our decision whether to go forward, rotate our angle forward or backward, is going to be a plus or a minus 1 according to which way we rotate our angle during each iteration. Okay, so we'll talk more about this term in a minute. Okay, so it turns out that you can remove these constants k sub I, because right now there's a multiplication in here that we don't want to have to do. So, and I'm not going to go through the math for this, but you could remove those k sub i's, which are for each iteration, so that we don't have to do a multiply here. We want to be able to remove these k sub i's. So here's what we do. Removing the scale constant from the iterative equations yields a shift add algorithm, which is this part of the equation. I'll show you how this is just a shift. This part here is a shift, and I'll show you that. And here's our add or subtract, whatever it happens to be. The product of the k of i's can be applied elsewhere in the system or treated as part of a system processing gain. And that product approaches 0.6073 as the number of iterations goes to infinity. Therefore, the rotation algorithm has a gain of a sub n of approximately 1.647. And this is due to pulling these k's out of this term so that we don't have to do a multiply during each iteration. And so collectively what happens is you get this overall gain a sub n, which is the product of each of the this from each iteration. So the exact gain depends on the number of iterations and obeys this relationship. It also needs to be noted that the previous equations are valid for rotation angles between minus pi over 2 and pi over 2. So from minus 180 to 180 degrees. So in order to increase the convergence range for all rotation angles where the z of o represents our angle, where that's less than pi, so we go from 0 to pi or we go from 0 to minus pi, Boulder proposed an initial iteration which rotates the input vector by plus or minus pi over 2. And the way we determine that is if the angle is greater than 0, then we are going to subtract pi over 2. If the angle is less than 0, let's say it's over here in this quadrant, then we're going to add pi over 2 to get it back into this quadrant. And here's what we do to x and y in order to do that translation. Our new x prime of 0 is equal to minus d times y0. Okay, where d is equal to 1 if z is greater than 0 and minus 1 otherwise. So here I have a vector that's in this quadrant here, and we need to do this initial pre-rotation and put it back into the minus pi to pi over 2 range. So we do that by subtracting 90 degrees, and that's what this equation right here is. ZO prime equals our initial angle minus d times pi over 2. So since d is a 1 if the angle is greater than 0, then we're going to subtract pi over 2. Okay, so if this were, say, 90 plus 10, then this would just be 10 degrees now. Okay, so that would be our new angle. However, you notice that the x and y are really not quite what you would expect here, and some of the texts that I've looked in don't have it right. They have one of the terms wrong. But in order to get the signs and everything to come out right, this is what you would use right here. So our x of 0 equals minus d, and in this case d is 1, so x of 0 is equal to minus y of 0. Now, in reality, if this were the actual vector, it would actually be, this value would be actually the same as y0. But what we want is to get the signs to come out right in the calculation, we have minus x of 0. You can go figure that out if you want to. But anyway, this is the initial pre-rotation that you do if it's in this quadrant or this quadrant. So we need to get it into this area in order for this function tangents, arctangents to work. So the elementary angles can be expressed in any convenient angular unit. You can use radians, degrees, or something else. And I'm going to actually show you how to use something else because it works out much more conveniently. So those angular values are supplied by a small lookup table, one entry per iteration, or they're hardwired depending on the implementation. The angle accumulator adds a third difference equation to the CORDIC algorithm. So here we have z of I plus 1 equals our current angle minus d sub I times the arctangent of 2 to the minus I. So this is known as our angle accumulator. Okay, and this ultimately, as we get to the very end of this iteration, it approaches 0. Thus, we now have a set of accumulation equations used for each iteration. Okay, the goal was to pull out those k sub I terms so that we don't have any multiplies during each iteration. So here we have our x, y, and z equations for each iteration. So here we have our next x, I plus 1, is equal to our current x minus our current y times d, which is dependent upon the angle according to this right here. D sub I equals plus 1 if d sub I is greater than 0. Otherwise, it's minus 1. Okay, so y sub I times d sub I times 2 to the minus I. So what is 2? If let's say d was a 1, for instance. So I'm going to multiply y times 2 to the minus I. What is that doing? Can anybody tell me? How would you do that in hardware, in Verilog?
Just a left shift or a selection.
Yeah, it's just a right shift. So we just shift it right the number of I, according to I. So this boils down, the whole thing is this boils down to a shift of y sub I, and this term turns out to be a shift of x sub I. So now what happens to either one of these terms, x sub I, d sub I, 2 to the minus I, when I is greater than the width of x, or y?
0.
Okay, so in other words, during our iteration, if we go more, if our number of iterations is greater than the width of our variables x and y, these terms are just going to be 0, so it doesn't do us any good to do more iterations than the width of the variables. Is that clear? So if y, let's say y and x of I were 4 bits wide. After the fourth iteration, these terms start going to 0, so they don't do any good. We're just assigning x sub I to x sub I plus 1 and y sub I to y plus 1. So we've gotten all the resolution we can out of it. Okay, so these are our set x, y, and z equations that we're going to use to make our calculations to rotate that angle. Okay, and remember, because we pulled those k sub I terms out, we have this overall gain of a sub n. Okay, so here we have, here's what we get. Here's the equivalent of what we get by doing this iterative process. We basically get the equations we wanted at the beginning, but we just have a gain tacked on to the end of them. And that gain will approach the 1.647. Okay. Okay, so here are our equations. This is what we're approaching, and our angle approaches down to 0. We start off with some value, and it approaches down to 0. So far we've seen that we could create a CORDIC function that could be used to rotate vectors, but what good is it so far? We need to do something with it. Well, notice what happens if we define a vector where x sub 0 equals 0. So let's say that this x sub 0 is set to 0. Okay? Just think of this as a block, and you have inputs of x0, y0, and z0. And the outputs are the x and y. Z we don't care about. That's just an internal thing we're using to get to our destination. So if we set x sub 0 to 0, notice that this term and this term here go away, and we have the equivalent of minus a sub n times y sub 0 times sine of z0, and we have a sub n times y0 cosine of z0. So here we've created a function now that can produce products with sine and cosine. If we were to set y0 equal to 1 over a sub n, the rotation calculation that we've just created produces the unscaled sine and cosine of the argument z0. So that's one purpose you could do for it. But very often, though, the sine and cosine values modulate a magnitude value, okay, like this y0. Using other techniques, such as a sine and cosine lookup table, requires a pair of multipliers to obtain the modulation. The CORDIC technique performs the multiply as part of the rotation operation, and therefore eliminates the need for a pair of explicit multipliers. So here's what you might have in a conventional digital down converter. You might have your signal coming in, maybe it's run through a bandpass filter or something, and you're going to multiply that by a cosine function and by a sine function, and you're going to produce equations like this where your angle function is your 2 pi f oscillator over your sampling frequency. And you might have a ROM lookup table. That's what this represents. The disadvantage here, though, in doing this method is that you effectively, I'm just saying effectively, or about, that's what this is, about 2 to the n times n bits. So you have a very large lookup table if you do this method. So an approach to, yes?
But that's basically a DDS, right?
Excuse me? Let me back up.
The block you just described is basically what I would call it, you know, like a direct digital synthesizer.
Yeah. So this method, though, what I want to show you is the difference between this method and using a CORDIC as far as the amount of data that you have to have. So an approach to overcome this drawback is the calculation of the corresponding sine and cosine value by means of a CORDIC, with the main advantage of using a small lookup table, which will be somewhere in the neighborhood of n by n bits. So the major drawback of the CORDIC approach is the increased circuit complexity. However, if it's used in the context of a digital down conversion or frequency synchronization, the additional hardware effort is partially compensated because there's no need for explicit multipliers. Okay, so here by feeding the right inputs to the CORDIC function, we can get our sine and cosine values. If we set x0 to 0, we'll have these equations. Okay, so this will allow us to make a CORDIC version of it. So here I have my block. This is my CORDIC function. I feed 0 in on the x, okay, and here's my signal coming in on the y, and for the z, my z0, I feed in this 2 pi f, where fo is my oscillator frequency and fs is my sampling frequency, and I'm going to get these equations coming out over here. So at each clock interval, y0 is loaded with the current sample, that's right here, of an IF input signal, and z0 with a current sample angle, that's this one, and the latter is supplied by an overflowing phase accumulator, and I'll talk about this phase accumulator when we get into the implementation of the CORDIC function. So the overflowing phase accumulator, which generates the oscillator frequency f sub o, x sub o is set to 0, and then after n+1 iterations, the quarter provides the samples I sub k and q sub k of the down-converted in phase and quadrature phase signals with a resolution of approximately n bits. In order to achieve this, only a very small lookup table is needed, and it'll contain the n+2 basic rotation angles. That's why I said it's about equivalent to n by n. So the difference here is n versus 2 to the n. And you get a much smaller amount of data that you need to have. And you can do that right in your design pretty easy. Okay, and so the table in here is basically just a table of those arctangents of 2 to the minus I that we need in order to calculate our rotation angles to approach 0. So we're going to start with z0 and it'll finally approach 0. Okay, still though, the main problem of the CORDIC is that the n+1 iterations have to be performed for each signal sample, requiring an internal clock rate being n+1 times higher than the sample rate of the signals. However, if we implement this CORDIC so that it has a pipelined architecture, it'll eliminate this n+1 factor, so you run it at the same speed that you're sampling. So that's where it becomes suitable for high-speed applications. An additional advantage of such an implementation is that there is no need for a lookup table anymore, since the invariant elementary rotation angles can be hardwired to each pipeline stage, and I'll show you that in the code later on. So in other words, it's just a small table, and each element of the table is applied to a particular pipeline stage. So let's look at the actual CORDIC function itself. And here's the receiver.v. This is just a portion of the file here. I'm going to show you out of receiver.v. Then I'll show you the CORDIC function. Right now, in your current SVN version of Mercury, they're using a function called CORDIC. And you can look at that one. That one was written by different people. Different people made changes to it. I wrote one that I'm going to show you today that's fairly similar to it, does the same thing, and I have it running on mine right now, and I just gave it a different name called CORDIC. And basically the function is just has a clock. It has the xn data, the yn data, this frequency data, and the x out and y out, which becomes the I and q. And this one did it a little differently. It just had just the n data. So my function is a little more generic in that it has both an xn and a yn. And I feed the xn the n data, and I feed the yn a value of 0. Because I'm going to use the CORDIC in this method to produce my I and q. You could use the CORDIC for other things if you wanted to, but I'm using it in this particular manner. So now let's look at this actual CORDIC function itself. So it has a couple of default parameters. One is called the in width, and that's the width of the analog to digital converter data coming in. Then we have these extra bits, in this case 6, so this gives us better resolution and noise reduction. Then you'll see that there's some local parameters just defining like wi is equal to the in width, and I use it down here to define how wide the xn and the yn are. They're equal to whatever the in width is. And the out width will be this wxy, and that will be the in width plus the extra bits, be 22 bits. So the number of stages then is going to be equal to, I'm going to set the number of stages equal to that width, because if I go beyond that, remember those shifts are going to go to 0, so it's not going to do any good to go any further as far as the number of stages of iterations. So I'm going to set the number of stages equal to that same in width plus the extra bits. So here we have our clock is our input. We have, and I call this actually the phase step. Okay, and it's actually a ratio of f0 over fs, and represents a range from 0 to 2 pi, and I'll show you that a little more later. So it's a number. This phase step is basically a number that goes from 0 to this right here, 32 bits of ones. So it's 32 bits wide. Okay, so we've got our x and our y in and out. Then in the next set of code, the next block is basically just a arctangent table lookup. So I'm going to choose my values such that the upper 2 bits are going to tell me what quadrant I'm in. Okay, so this value right here, which I'm not using, I'm just a comment here. This value, I'm going to let this represent 90 degrees. Okay, remember I can choose whatever, I can use radians or degrees or whatever I want. I'm using the whatever I want. And you'll see that in both CORDIC functions. So I'm going to let this value represent 90 degrees. So that means that this value would be 45 degrees, which is the arctangent of 2 to the 0. Is this clear so far? Okay, so if this, go ahead.
So your angle is going to turn out to be 1 over 2 to the n of a circle. Is that correct?
Yeah, a complete 0 to 2 pi would be a value of all these bits 0, and all the way up to 2 pi, all the bits would be 1. Okay, so that means that this value right here would be 90 degrees. First of all, is that clear that I'm just letting this represent 90 degrees?
Yeah.
Okay.
Yes.
So, and if I were to have 180 degrees, this would be a 1, 0. And then a 270, I'm sorry, yeah. 1, 0, and then so on. Okay, anyway, so this would be 45 degrees because it's half of this. And then this number is what would actually represent the arctangent of 2 to the minus 1. In other words, 26.565 whatever degrees. And it's just, you take this number, divide it by 45, and multiply it by the 26, and you'd get this value right here. So I'm just making a table of all of these values of my angles until I get down to like here 30, which, you know, it's all gone. But it turns out we're only going to use up to 22 of these for now because of our data width being 22 or whatever. Okay, so this is just, all this is just a table of all the different arctangents of 2 to the minus n. Okay, then the next thing we create, this is we're going to look at all the code for this CORDIC. We're not missing anything. So here we have our x, y, and z. Notice that this is the width of x, this is the width of y right here, the wxy. Okay, and I'm creating pipeline stages. In other words, this is the width right here, which is going to be the 22 or whatever. And then this is the number of stages. So this is how many of those I'm creating. One of these wide for every stage. So we create our x, y, and z. Those are our declarations. And here z, I'm setting it to 32 bits wide, and we're going to have 0 to 21 or whatever of those. And then I also create what I call the phase accumulator. It's 32 bits wide. Then the next part of the code is for our very first stage. So here I've created a thing called quadrant, and all I'm doing is just looking at the upper 2 bits of the phase accumulator. It'll tell me what quadrant I'm in. And here I've created signed values called nxn and nyn, and all they are is the negative of the inputs in case I need to use them, which I do down in here. Okay. So the first thing we need to do is we need to make sure that the rotation angle is in the minus pi over 2 to pi over 2 range, and if it's not, then we do our pre-rotation. So how do we determine whether it's in the minus pi over 2 to pi over 2 range? Well, we look at the quadrant. Which quadrant is it in? Okay, so let's see here if I have Okay, well, I'll show you in just a second. Anyway, if I determine that it's in this 0, 0, this would be the quadrant from 0 to 90 degrees, and this 1, 1 is going to be the quadrant from 270 to 360. In other words, or the minus pi over 2 to 0. So if I'm in those, I don't have to. If I'm in those two quadrants, I don't have to do any pre-rotation. Okay. If I'm in the 90 to 100, or from pi over 2 to pi range, or 90 to 180 degrees, that's what this is, then I'm going to have to do a calculation. And if I'm in the other quadrant there, I'm going to have to do a calculation. So let's look first at the two quadrants where we don't have to do any calculation. So remember, we created our x, y, and z. So we're going to set up the 0th stage. We're going to set those, and they're going to be equal to the data coming in. Well, since our overall gain is the 1.647, we want to divide the input by 2 and then multiply by 2 to the extra bits. So that's the same as doing a shift left by extra bits minus 1. So our extra bit value was 6. So if we take and we divide by 2 and then multiply by 2 to the 6, it's the same as shifting left 2 to the 5. Okay, so that gives me this is actually a 22-bit wide value here. So basically we're just setting it up. Now all I've done here, if you look at this concatenation, all this is when you divide by 2, it's the same as shifting right by 1 bit. So I'm holding the most significant bit of xn, that's the sine bit. I'm just replicating it here and then using x of n and then shifting left by 5 bits. So that gives me my 22-bit value. And I set z of o to the phase accumulator, which starts off at 0. So that's just the initial setup, assuming they're in the minus pi to pi over 2 range. If it's not, then I have to do the pre-rotation according to which quadrant it's in. Okay, and this would be the pi over 2 to pi quadrant. And so for y, I would need the minus value of it, and that would be assigned to x, and y of 0 then gets assigned the value of just the positive value of x that comes in. And then the phase, we have to subtract pi over 2 from the phase accumulator. Well, since the upper 2 bits of the phase are the quadrant, then I'm just going to 0 those 2 bits, the upper 2 bits of the phase accumulator. That puts me back into, that basically does a subtract pi over 2. So I can just clear those 2 bits and then use the rest of the phase accumulator bits, and that gets assigned to z0. Then similarly, if we're in the minus pi to minus pi over 2 quadrant, that's this one, then x of 0 gets basically assigned the y, the positive value of the y that's coming in, shifted right once and then shifted left the other extra bits. And the y gets assigned the minus x. And then since we're in this quadrant, the minus pi to minus pi over 2, if we set those 2 bits to 1, 1, that puts us back, that's the same as adding pi over 2 to the phase accumulator for this quadrant. So I just forced those upper 2 bits to that. And then our phase accumulator is basically every iteration, every clock that this thing's running on, our sample frequency, it just keeps adding this phase step. Okay, so eventually when it gets around the 2 pi, it'll just overflow and it'll just start over at 0 again, keep going around the circle. This phase accumulator is a 32-bit wide, just like our arctangent values, and so 0 represents 0 degrees, and when you have all ones, that basically represents 2 pi, and so if you just keep adding that step, it'll just keep going right around the circle. So let's look at it. So what is fed into this phase step, this is what comes into the CORDIC. It's basically a ratio of our our oscillator frequency divided by our sampling frequency, which is 122.88. So that's the calculation. However, it's represented. Okay, I'll back up. That's what's fed into phase step. Now, you remember if you looked back at the block diagram that we had earlier, the phase that you feed into the CORDIC function, the angle I mean that you feed into it, would first be 0, then it would increment 2 pi f0 fs, 2 pi f0 fs times 2, this is times 1, so on, times k. So we're basically doing that, but all we're doing is doing an addition here by just adding the phase step over and over. So we're basically going around the circle. I'll show you that some more in a little bit. So then, after we've done our initial stage 0, then we need to do all of our stages from 1 to S stage minus 1. Okay, we need to do the rest of them. And these are fairly simple now. Okay, here we have a generate statement. And I don't know if you've used the generate statement very much, but basically what it's going to do is we're using a for loop here, and you see that there's a begin and end block. Okay, and it's a named block. I called it XYZ. So the generate is going to take everything in this block and repeat it STG times. So it's just like replicating it, except when it replicates, it's going to be based, I've got stuff in here that's based upon the value of I. So let's look at what's in this begin and end block now. First of all, I have a wire declaration called Z sine. So when this whole block replicates, let's say it replicates 22 times or whatever it happens to be, the Z sine for the first block is not going to be the same Z sine as the second block. Okay, it's inside this named block. So remember, the scope of the variable inside of here is only local within this block. Nobody else can access that. Okay, so Z sine will be different for each block that's generated here. So just look at it as this begin end block of all this Verilog in here replicated this many times, STG times. Okay, so what do we have in here? Well, we have this Z sine, because we need, we need to know the sine of the angle as we go through our iterations. And I've created the signed values of x shift right and y shift right. And they're the width of our x and y variables. So here we do a simple, the x shift right for each iteration is going to be equal to the x sub I. Remember, it was x sub I times d times 2 to the minus I. Well, that's the same as x sub I right shifted I times. Now in this case, I'm using a signed shift right. That's a regular shift right is just 2 of these. Okay, but this is a signed shift right. If you don't use a signed shift right, because we're working with signed values here, then the bits that get shifted in will be 0. So you have to do a signed shift right. Now in the other CORDIC function, when they did it, they may not have had this operator available, since this is a newer operator in the Verilog 2001. So I went ahead and used it in my code. But if you look in the old code, you'll see that they had to replicate the MS bit and then shift the value and do some concatenations and stuff. And so this is much simpler looking, just to have the sign shift right. So here we have our x and our y values that we sign shift right. And then the sine of the current rotation angle is equal to z of I, the most significant bit of it. Okay, and if the most significant, if z of I is less than 0, then that most significant bit will be a 1. Okay, so 1 for this value means that it's less than 0. So then we have an always block. And this is and you notice it has non-blocking assignments, so we're creating flip-flops here. And so here we have our basic CORDIC equations. So here we assign our next x is equal to our current x and y values depending upon the sign here. And the sign, okay, if we have a negative angle, this will be true. And so it'll be x sub I plus the y shifted right. If it's a positive angle, then it's x sub I minus the y shift right. Okay, so this sine is just determining whether we do an add or a subtract. Either one of these equations, depending on the sign. Same thing for y, and the similar thing for the z. Okay, so if this is a 1, which means it's a negative angle, then if we have a negative angle from 0 to minus pi, then we want to, if it's just a negative angle, then we want to add what's in the arctangent table. Otherwise, we subtract what's in the arctangent table. So that's our whole, this whole thing is just creating all of our stages, pipeline stages, because each stage is registered. And so each stage is using a different value out of that arctangent table. And that's the whole basic CORDIC function right there. And then so the output of x and y is just the final x of the last stage and y of the last stage. And that's it. Now, before I go on, I'm going to show you an example of this. Is there any questions on what I just went through?
Well, Kirk, this is Steve. There's not any rounding here. This is all truncation.
Yes.
So there's going to be a small error at each of the entries in the table. And so what's the effect of the error accumulation here? I've seen some of the CORDICs that are used in like QSR1 and so on. Some of these actually have added or subtracted the virtual equivalent of a half in the low order bit to do rounding.
Yes.
What if you don't?
Okay, I generated this one just so I could show you the basic principle of how this works. Now this actually works. I'm running it on my Mercury right now. I don't know what the actual error of this one is versus the one that's in SVN right now that's called CORDIC.v. If you look at the one called CORDIC.v, you'll see that it does do some rounding. So if numbers are negative, it does one thing, and if they're positive, it does another. But basically, yeah, it uses a bit just below the last one that you'd normally be using to do the rounding.
Right.
So these equations don't have any rounding in them right now.
Right. So I think one on the I'm not sure of the history on Mercury on the QS1R that was derived from it. It also didn't have any rounding originally, and I think there were some 90 dB down spurs or something like that got eliminated when they put in the rounding. So it is quote way down in the noise, but there was there were discrete spurs that got generated from it. So
yeah, I would like somebody to. This is actually in the latest test code release that I've put up on verilog.hpsdr.org in the April 7 release. I think I have on there right now. I would like people to actually try this out and see if they notice any difference in the two. I didn't so far in what I've been doing here on my desk. So the ones that you have in SVN right now, they have the rounding stuff in them. But if you'll just for fun try this and do a comparison, I'd be interested to see what people come up with.
And rather than doing rounding, couldn't you just carry it out an extra 1 or 2 shift registers?
I'm not sure what all the implications are on the rounding. I'd have to look at the math and see. I don't know. I haven't done CORDICs that much, so I don't really know. Okay.
I think what happens is that you get a periodic error if you don't round. The error depends on the phase increment, and you get a periodic error. It's very, very small, but
that could be.
But if you do the rounding, then that tends to cancel out, and you don't get the pattern that generates the coherent spur.
Yeah, it's hard to know because it depends on which way the rotations go each time and where you start. Yeah, I don't know. Oh, okay. So it'd be interesting if somebody could compare this and see if they notice any spurs in this versus the other one. I can put the rounding in here, but I didn't want to do that for today.
They will be very small.
Yeah. And I think this one is a little bit simpler and a little bit more generic than the one that's in the current SVN right now. And if the rounding helps, I'll put it in here eventually too, but I wanted to be able to show this in a simpler format.
It's the shortest one I've ever seen.
Okay, and I'm running it right now on my Mercury, and I couldn't tell the difference for what I was doing. I haven't done very much though right now, but be interesting for somebody to try it and ring it out and see how it's doing. Right now, let's see if well, if you look in the April 7 release in the receiver.v, you'll see that I have the normal one called CORDIC. I have it commented out, and I have this one, CORDIC, starting with the letter K. I have this one instantiated right now. So you could just comment one out and put the original one back in. It should be real easy for you to switch between the two to test if you want to try it. Okay, you don't have to use this one, but I just want to be able to show it. Okay, so let's look at some angles here real quick. Let's say that we had a we were rotating, like our FO over FS caused us to rotate 30 degrees at a time. So let's look at the here are the positions that we would have. Okay, and here are the cosine and sine values that we would have every 30 degrees. So here's the table. Now here's what I mean. This is our quadrant 0, 0. In other words, the most significant two bits of that phase accumulator are 0. And here the most significant two bits are 0, 1. So you notice as you count from 0, oops, I got these backwards here. They're supposed to be plus. I got those switched, sorry. As you count from 0 to pi, you go from a 32-bit value of 0 up to a 32-bit value of 0, 1, 1, 1, 1, 1, 1, 1, so on. Okay, and then starting right here, you have the most significant bit of that 32 bits set to 1, and the rest of the bits are 0, and then it counts on up all the way to all 1s for the 32-bit value. So you'll notice that this 32 bits of 0 all the way up to 32 bits of 1s is the equivalent of 2 pi. So here we have our original CORDIC equations, and here's what we have if we set x equal to 0. We have these equations. This is what it's going to produce. So let's assume that we've set x of 0 to 0, and we're going to set y of 0 to 10,000, just for an example, because I'm going to show you a simulation here, a simple simulation. So our a sub n is equivalent to another error there. Whoops. Our a sub n is 1.647. I wrote that wrong. I'm sorry. I just did this just before we started class. So our a sub n times our y sub n times 32. Remember, we divided by 2 and then we shifted left by 6. So that's the same as the shift left by 5. So it's the same as multiplying by 32. So that product right there is equal to 527040. That's the max. And then to get these different positions, you take that value and multiply it by the appropriate number here, and that would give you our position as we rotate around here. So let's go take a look at, see if I can get this. I had a little simulation I wanted to show. Model sim. Here we go. I created a real simple test case. Maybe I can upload this to the website if you want to play with it just to see it work. This is my test program, and I included both the original CORDIC.v and this new one. So we're going to simulate the two just so you can kind of see how they operate. So I just created this module here, and I'm going to set my x sub n equal to 10,000, decimal 10,000. Okay, so we're going to do this equation, and I set my y of n to 0. So now in doing this, I'm actually, instead of getting the minus sign, I'm getting the plus sign. So the x out is going to be the a sub n times x sub n times cosine of the phase, and my y out will be the a sub n times x sub n times the sine of the phase. Okay, and so I'm setting my 32-bit frequency step value to about 30 degrees here at a time. Okay, and inside the CORDIC functions, like in the one I showed you, I had this phase accumulator. I'm going to force it to stay at 0, so it doesn't just keep incrementing every clock. I want to force it to 0 so you can see some things here. And in the other CORDIC function, I'm just forcing its phase accumulator to 0 too. It had a different name. So then I delay some time so that we can see that it calculates that first one and holds it. Since I don't let the phase accumulator change, we're going to keep this phase at 0. Then I release those so that every clock the phase accumulator starts accumulating. So it'll go, so then it'll start going 60, 90, 120 all the way on up to 360 or back to 0. Okay, so I'm going to let it wrap around. Okay, and then I'm going to force them back to 0, wait some time and stop. So here I've instantiated both of the CORDIC functions. Okay, and so these xn and data and all this is set according to what I created up here, my xn and frequency, etc. Okay, and then the rest of this is just a clock. I created a 12 megahertz clock for fun here. So that's all the test does. It's real simple. It just lets it run. Okay, that's just the CORDIC function we looked at already. So let's compile. Let's go ahead and run it. Can you see this okay?
Yeah, it looks fine.
Okay, so it ran, it stopped. So let's see what it did here. Okay, so the first thing, there's our phase step, our 15555 whatever, our 30-degree equivalent value. And here it produced an x out of 526,969 and a y out of -1, which is really close to 0, you notice. Only 1 bit different. Okay, so the accuracy compared to the 32-bit value is quite good here. So that's the first value. And what did we calculate? Well, we calculated, let's go back to, let me go down here at the bottom. We calculated for this first angle of 0, right? So the cosine of this is 1 times this 527,040. Okay, that would be our ideal. Well, we're very, very close to that. Okay, and in fact, I think the error is like 0.0013%. I think I calculated off. Okay, so that's from the one I created, and this is this CORDIC.v. This is the one that's in your SVN right now. It did values of 2 and 526,962, which are very close also. So then you'll notice that I held that for a while, and then finally I released and let it start going through, letting the phase accumulator count up, and we're going to zoom in to see all those different angles there. Okay, so what we're interested in is this one here, this x out and this y out, and then the original ones, which are right here. So mine took a few more clocks to do its initial thing, so mine are shifted over from these. But if we look at this, in fact, let me put these, let's just put them down here where we can see them all close together. Okay, and let me put them in the same order. So here you see this is basically 0. This is the basic 527,040 right here and right here. Okay, so here and then this 263 and this 263, these are actually big numbers here. 263.45, versus the one in SVN right now is 263,481. So if you go through and you look at that circle and these values, you'll see that those values correspond to these points on the circle. So I just wanted to make a simple test, and you can check the sign of the sine too to make sure that the signs are correct, whether it's plus or minus. So you'll see that it actually did the sine and cosine functions properly. So if you like, I could put this little simple test thing up there and you can play with it just to see it. And then you can look, if you like, you can put more signals in and you can see what things look like at each stage in the x and y. So here you'll see the x, y, and z. But if you let's put my cursor on here, you'll notice there are 0 to 21 different stages here. So those are all of the calculations through the different stages for x, and then here they are for y, and then here they are for z. So you can see z changing till it gets down to basically 0. Okay. So that's mostly what I wanted to show you. There is one more thing if I can get it to run here. And just a minute. I need to get another virtual machine running here. Okay, are there any questions during this time, or did any of this make sense?
Yeah. As a first pass quality check on this, could you take the output data, run it through a Fourier transform, and then actually, with a lot more as much resolution you need, and then look for the spurs that people were talking about that might also be there as as a result of lack of the round off error? Is that kind of the first step validation on something like this?
You could. I haven't done that, and I don't really right now have the time to do it. But if somebody would like to do that, it'd be kind of interesting to see the results.
Because I assume the errors would show up in a granular enough Fourier transform.
I don't know. You could just take and maybe run it, and well, no, I don't know. I'm not sure what the best test would be for this. But if somebody would like to actually do something like that, I'd be interested in seeing how they do it.
Okay.
Where are these spurs? If I were to go looking for those spurs, are they close in, far out, or where?
You talking to me?
Yeah.
Whoever knows about the spurs.
Okay.
Yeah. Yeah. Spurs are DC. There may also be a DC offset issue as well from the rounding. Places to look there in the two places in GNU Radio. There was some discussion of rounding, which they don't do in the US in the USERP either. And then in the QS1R history chats, there was some discussion of it probably 7 or 8 months ago when they switched over to doing rounding. There was somebody who had detected the difference. So I would just go searching in those archives first. And I'm not sure. I think that they are just. I think if there's something discrete, it would be the position would be dependent on the phase increment. So it would move around if you move the phase increment. So I'm not sure if it would be close to the baseline or close to your F sub O, or whether it would be someplace else. It would just be at a constant location dependent on the phase increment.
Now you mentioned, I think you mentioned there was a DC offset. Explain what that was.
I think that they were doing essentially doing a truncation instead of a signed, a biased round. Like if you round away from 0,
right.
So negative numbers become large, more negative, and positive become more positive, then you don't have any issue that could possibly arise with a DC offset. If everything is rounded in a positive direction, or if it's truncated but you're only working in a positive quadrant, then you could end up with a bias that pushed you away from DC. So I don't remember that one, unfortunately. I don't remember very well, but there was some discussion of that.
Do you know
I
how
think
it showed up? I
in the
mean,
user.
what the
I'm
symptom?
sorry?
Do you know what the symptom was that showed up when it had that problem, the DC offset?
This was in GNU Radio. People are often doing these weird algorithms. Essentially, what it was things like they were attempting to do a correlation or a phase lock loop or something, and what was happening was that this DC offset would show up as when they did a correlation of two what should have been matching waves, instead of it being either +1 or -1, there would be a very slight positive residue when it should have been a 0 residue. So it was tricking somebody's code. It's the only reason anybody noticed. I don't think you'd notice it if you were just using it for radio.
Okay.
They were doing some digital signal recovery type stuff where it actually made a difference.
Yeah, I'm just kind of curious as to if this particular one, because I just created this one. It's very similar to the one that's in the SVN right now for Mercury, but just curious as to how well this one's working.
Yeah, the errors are tiny. I mean, there's no question about it that this is going to work really well. It was real. I think it was really just people who were using test inputs, and I think you probably could do an FFT and detect it, but I don't think anybody did that. I think they were really just using near the noise level sort of test data, and they saw these spurs that were unaccounted for. I'll see if I can find the references and I'll mail it to you, Kirk, and you can fan it out if you want to.
Okay, that would be good. Thanks. Looks like we're approaching 5 o'clock here, so I don't really have too much time. I wanted to talk to you some more about clock domain crossing issues because I wanted to make sure that you understand the difference of how to take care of clock domain crossing issues when you go from a slow clock or a slow domain to a faster domain, and when you go from a fast domain to a slow domain, because you have to do things a little differently there. And we don't really have the time for today. Maybe I'll do that in the next one, but I will show you this tool real quick. That's Minter has a tool. It's called 0N CDC, and it will actually check for some of these CDC errors. And let's see if I think it's already pre-compiled here. The other day, before I released, I think the April 7 version, it actually caught a CDC issue that I had created. And what I had done basically was a typo. I wasn't paying attention. But this tool, when it catches CDC errors, these are things that, okay, ModelSim's not going to catch, your compiler tools are not going to catch. They're not geared for doing these type of things. So this is one tool that you can use to actually help you find those clock domain crossing issues. And some things it'll warn you or flag you about that you just manually check, and you'll know, I mean, you have to know whether or not it's implemented properly. But it will catch things. Let's see if I can find this one here. Can't remember. Okay. Okay, so I had this violation here, and it said missing synchronizer. So, is this the one? Yeah, this is the one. So I got to looking. I was like, okay, here I'm creating this reset. And remember, and I've just started kind of going through the code and doing more cleanup where I'm starting to put these prefixes on my signal names, and I suggest doing that. I didn't do it originally in this code because I was just trying to get it converted over, and I wanted to kind of get things done, so I didn't go through and put all these prefixes on, but I'm starting to do some of that now. And so in this case, my C12 underscore prefix means that this signal is in my 12 megahertz clock domain. Okay, whereas the IF underscore prefix is for a different domain. So what do you notice here immediately about creating this C12 reset? That's a problem. Anything? real short little statement here. I'm clocking it from a C144 clock domain, which is 144 megahertz clock domain. I want to clock it into the what I'm calling my C12 clock domain. So what's my problem?
What's in an at positive IF clock block?
Yeah, I don't have my C12 clock here. So it was a typo. I should have had C12 clock because that's the clock domain I want it to be in. So it caught that. Okay. It doesn't care what prefixes are. It just sees that it knows what the clock domains are, and it can tell. So that was one that it caught for me the other day. So anyway, it's an interesting little tool. I just started playing with it the other day. I thought you might be interested in that. Yeah, I wish I had more time because I want to go through some of this clock domain stuff again, show you some examples that are actually a specific example in Aussie of going from a fast to a slow domain and the problems you can get into. Okay, so I think that's about it for today. Unless we have any questions, we got time for a little question.
Well, I have a comment.
Okay.
Every time I get new code from you, I've been running the April 7th code now. These boards are starting to sound absolutely fantastic. So and some of the people I have over have noticed.
Did I lose you?
Push the wrong button.
Okay.
I have lots of mute buttons. I think there's going to be some clamoring among the SVN folks to get their hands on this code if they hear how good it is.
Well, actually, I've been working with Phil Harmon a lot on this, and he's testing it. He says there's a couple little issues I have right now, so he hasn't released it yet with Penelope, because I haven't done any testing on Penelope. So if people could test Penelope and send me any feedback on that, I'd sure appreciate it right now. In my setup, I don't have an antenna right now set up to test Penelope.
Yeah, I have not yet been able to get any audio through Penelope. I did get the push-to-talk line working, but that's as likely as not to be something I'm doing wrong here.
That's interesting you say that push-to-talk's working, because Phil Harmon is telling me that my push-to-talk is always on for some reason in his setup, and I don't know what's going on there yet. He's going to look into that some more.
Well, maybe he ought to exchange experiences with me. I'll have to send him a message because mine's working fine.
Okay. Or maybe there's some interaction where it works in one and doesn't in another or something. Anyway, I need more testing time on Penelope. Should I post this little test case in case people want to look at this?
Oh, absolutely.
Okay, I'll do that. I'll post it probably a little later this evening here. And then you can play with both CORDICs and experiment around with them. So all I wanted to do here was just test that the sine and cosine were functioning properly.
I wonder why the zero-in tools are only available for Unix operating systems.
I think
there is no Windows version of that.
Right. I think there was a third party that did it, and maybe they did it for security reasons or something. I don't know. I don't know.
In any case, if after seeing more of the zero-in stuff, anybody else wants a copy of that, that's also available as an AMSAT tool. So just get a hold of me at W2GPS at amsat.org.
Yeah, I was glad I could start trying it and experimenting with it, because I wanted to specifically try it on this project to see, am I missing, things? And sure enough, I was.
Yeah, that's what these tools are for. They're for education. There's no limit on the education.
Okay.
Or the purpose of the education. And there's a huge list of tools. Are there any others you think might be interesting?
I know they have some FPGA tools. I haven't tried those. Were they precision something or other? Precision RTL or precision synthesis or something like that?
Yeah, I've been concentrating on the PC layout tools myself, but yeah, there's lots of FPGA tools in that list, and I haven't got a clue what they all do.
So this is one that I've been wanting to try for some time, but just never had the opportunity. And so now I'm getting to do it, thanks to you.
Yeah, well, it looks like you caught an important bug.
Yeah, I did. So it was kind of neat just to see that, hey, it really does catch things. So, and this was in my code the other day, and the code you have, the code that's up there now doesn't have this in it. This is in the aussie-janus.v. So it was just a typo. I get to going along. Or what may have happened is I may not have had the prefixes on the signal. It may have had a different name with no prefix, and that's why I've kind of adhere to using prefixes when you're doing FPGA design work that has multiple clock domains, because visually you catch it. Without the prefixes, you're visually not going to catch it.
The other thing, if others aren't yet doing it, download the new Power SDR, because if you're testing, it's wonderful because now you can physically turn on and off the hardware without ever leaving Power SDR, and every time you hit the start button, it just reloads it, so you don't have to get out of the program every time.
Oh,
Yeah, that's one of the key changes in this latest version that they did that was done for us.
okay. Do we want to have any more of these webinars? If we do, what do we want to cover? And I would like to have maybe a short one on a little more on the clock domain crossing issues, if anybody's interested in that.
Anything you want to cover, I'd like to attend more of these seminars.
Okay, well, basically I'm going to need, at this point, I'm going to need some feedback as to what specifically you would want to see in a seminar, what people would want to see.
Is there anything unique in Penelope that we kind of a module that doesn't appear in Mercury that might be interesting, or maybe just a very high level walkthrough on Penelope's organization?
Well, that's true. I haven't done that, and the CORDIC in there is going to be a little different, and there's going to be filters that are a little different, maybe. Yeah, we could probably at least go through a top level view of it. Maybe we can
maybe kind of a compare and contrast, or top level, and kind of a we've looked at a lot of the modules as we've requested. Thank you. And then the next thing would be maybe, okay, so you take these modules, and one way it's organized is a Mercury, and then what's with compare and contrast Penelope.
Okay, yeah, maybe we could do that in the next one.
Is it? I know it's not associated directly with these boards, but is it possible to do a presentation on polyphase filters?
That would not be my expertise. Would somebody like to do that? I mean, I don't have to be the one presenting all the time.
Well, you're good.
I have my limitations. Well, if no further comments or suggestions, I think that wraps it up for today.
Oh, did you rewrite the CORDIC for Penelope, or are you planning on it if you haven't?
Oh, I haven't actually looked into it. I'm just using the one that was there originally. Yeah, I will look into that. Let me write that down here. Okay.
And I guess you need to look into possible rounding issues as well.
Yeah, I'll look into that. From what I mean, I haven't noticed anything in the receiver portion that this is in. So I would like people to test it, see see if they notice a difference, because it would be real easy since you have the April 7 test code to put either one in. I've just got one commented out versus the other one. You just have to comment one or the other out and recompile.
Yeah, I think I'm going to have to take it off the air and use test equipment to try to generate signals that might show some spurs to see if there's anything visible. But until I'm sure what to look for, it might be hard to know.
Yeah.
I haven't seen anything interesting lately. The signals are looking cleaner than ever.
Well, it would be really interesting to me to see the difference in the two, if there is a difference or not. And if anybody has a way that they can test that, and show us some results, that would be really good. And if I need to add in the reduction, if you want to use this one, if I need to add in the rounding, then I can do that pretty easy. I left it off today just for simplicity. So can anybody try that?
I'm just in the process of getting my Penelope and Mercury updated, so to get it all back in its box and working first.
Okay.
Another thing I tried today, not because I wanted to, but because I had to for other reasons, I started swapping the boards around, which, as we all know, with the SVN code can get you in a lot of trouble. I could not find any combination of moving the boards around that gave me any trouble at all at the moment, either with Mercury or Penelope.
Oh, that's good, because nobody's told me whether or not that worked yet.
Well, I haven't done a rigorous test, but I did start swapping them around more or less randomly, and it just kept working.
Huh. Okay, good. That's kind of what one of the plan was for this.
That's very good news.
And I'm also working with Phil Harmon right now to, we've got to get Janus so that it will work with this too. Right now I've just been testing the Mercury and the Aussie and the Penelope and making the code changes for that. So I have
another big one for some of us is 2 Mercuries.
Oh, 2 Mercuries. Okay. Yeah, something's going to have to be done in the power SDR for that.
Oh yeah, the protocol on the USB is going to have to change, right?
Well, for me, now that I have this design, it's not going to be very hard for me to add in another one.
No, I looked at it and it looked real easy from an FPGA point of view, but we're going to have to do something with the USB protocol. I haven't even looked at the protocol spec lately, but you got to get all those extra bits over there, and then you got to do something with them when you get them over there.
Well, right now there's a frame of data that's coming, say, from Mercury, and so that frame now, the amount of data, doubles basically. And then somebody at Power SDR is going to have to pull that data out and determine, pick which is which from which receiver and process it. And then we get into issues of how much data we
already
can.
Doing that. The Flex 5000's got 2 receivers.
Well, if somebody can tell me how to create the data frame from the FPGA to the USB, what they would like, then we could do it.
Well, I suspect the Power SDR 5000 software is very significantly branched from what Bill Tracy is maintaining for us.
Yeah, I'm just thinking that whatever they did to accommodate the second receiver, we could emulate that if we find out what it is.
There's a couple things we can actually do for future is not only having a physical second Mercury board, but actually having 2 receivers or N receivers in the current board. Of course, you're still using the same antenna. I know some people, they want to use different antennas.
Yeah, diversity reception is one of the key goals of the second receiver.
Right.
Is there room enough in the FPGA to implement a second receiver from a single antenna, like an
Yes.
80 and 40 meter pair? Is there enough room in the FPGA to do that?
I think there is.
Because that's a total duplication in the FPGA of what's already there, right?
Yeah, I just have to basically duplicate. Here's what I'd have to do a second one in Mercury. Right now there's the module called receiver.v, okay? And you feed it, one of the things that you feed it is the frequency. Okay, and I get that frequency. It comes from Aussie, it comes across one of the N wires through what we call the command and control data. And so Aussie is broadcasting this command and control data out to everybody. Well, Mercury picks it up and it selects the things that it needs out of that data, and one of them's the frequency. So we'd have to send a second frequency, so that shouldn't be any big deal. And then I'd have to instantiate another receiver.v that used that frequency. And then I would have two sets of data to send back to Aussie to send on to USB and up to the power SDR.
Yeah, and at that point, you got the same problem as you would have with separate Mercuries.
Right. So it's just a slightly, different problem there, but similar. So we're kind of set up for working toward that in hardware right now. I don't know anything about on the software side where we are.
What percentage of Mercury's FPGA is being used?
Ooh, I haven't looked lately. It's getting up there. A lot of the problems you have is it's not like you ever use an FPGA to its fullest extent. The problem is you get fuller and fuller, and most FPGAs are routing resources, and you start getting into timing issues because you start getting it too full. It has problems routing and stuff.
Yeah, some of my DoD friends told me anything above 40% is pushing it for them.
Yeah, I don't know where they're coming from because I've used a lot of different ones, and I'd say I push them more like 70%. It depends on the speed at which they're running them too. But I know, like in some of the Xilinx stuff, I was using some of the big Xilinx parts. I was running most of the stuff in there at 100 and something megahertz. I can't remember now, and then some at 200 and some at 400 megahertz. And I was in the upper 70 percentile of the usage. So yeah, good range is probably 40 to 70%. That's a nice range.
I'm looking forward to the day when I can do a design of my own that isn't derived from somebody else's work, that says that I understand all the stuff you've taught us.
Oh yeah, it just takes practice is all, and it never hurts to borrow other things to start off with so you understand what's going on. That's the way I do things.
And Kirk seems to write some of the cleanest code I can imagine.
Kirk, you told me you do not own the book Advanced FPGA Design by Kiltz. Is that right?
No, I don't have that one.
Because everything you do, including today's CORDIC algorithm, is done as though you were the author of that book. I think you and the author of that book would get along famously.
I've never seen the book. Let's see, the books that I have, the one I use probably the most here is this, what is this one? Verilog HDL, A Guide to Digital Design and Synthesis by Samir Palnitkar. I'm not sure how you say it. Indian name, I guess. And it's sort of a dark green colored book. And then I got let's see, there's an older one here by Thomas Morby. I think I had another one, but I think that's the only hardbacks I have. Oh no, I do have another. There's another Morby one. No, it's a hardback. No, I've never seen that book.
Well, I made the mistake. I was over at SAIC, another defense contractor, and we were talking about all this stuff, and what I'm learning from you and other places. And I was complaining that on a, not an FPGA level, on a signal processing level, I was having a problem getting my arms around decimation and filtering. Not so much the problem, I understand the filters you were describing, the CIC filters and the FIR filters, but there's more, and there's more things I want to do than just sideband signals. And I want to do polyphase filters, and I want to do other things. And I was complaining that my best book on that subject only had a chapter on it, and it was highly mathematical and didn't explain much. And they all brought out the same book. It turns out everybody over there owns the same book, a whole book on that one chapter. The whole book's multi-rate signal processing for communication systems. So there's whole books on just little chunks of the HPSDR code.
Yeah. Yeah, I need to get me probably another book like that. I'll do that when I get back to work again.
Well, actually, I had very slow sales from September to now. Sales are just now picking up, and I took advantage of that time to start reading these textbooks cover to cover.
Yeah, I've been spending some time now since I'm out of work right now. I thought it was a good time for me to do some of this stuff and learn some things. And so I've learned a lot from this project, so this has been really good for me.
I find the instructor learns more than the students sometimes.
Could be.
Well, good job. I guess it's time to go get a late dinner.
Okay.
Yeah, I'm on East Coast time.
And I don't know if my moderator is still on here, but I guess we'll sign out. I don't know how we do this. Okay, well, I'm going to sign out. If anybody has any questions or comments or things that they would like to see in the next seminar, just send me an email and we'll go from there.
Okay, good evening all.
Okay, good night.